Okay, in this lecture, we are going to introduce the concept of impedance. And we are titling this Impedance to the Rescue. And here we have some very distraught students, and they're saying, save us from differential equations. And impedance will come and rescue you and return you to the comforts of algebra. Here's our comfy algebra couch, and we want to return to our algebra couch because it was cozy there. These differential equations are just not friendly. So this is what we're going to do. We're going to take this kind of abstract approach for a moment, and I'm going to present this voltage source, V, and we're going to pretend that we can produce this signal, even if we can't physically in the lab for all cases. But we're going to take this signal, V equal to A, some scalar, times e to the st. All right, now we've seen this. We've been trying or applying this type of functional form, e to the st, to solving our differential equations. So this should be familiar to you. But let me just point out or highlight that this function is pretty flexible. It can encompass several different types of signals. So it can encompass a DC signal. DC, this is the value of A. And how do we do that? If we set S to 0. So we would have A e to the 0t. Well, this is just A, some constant, right? We can also have a real exponential, right? Something that would go like this. And for that, we would have S is equal to negative real. We could have an exponential that grows. If we have a positive real, that would be valid as well. And we can have, I'll say, complex sinusoid. And this is where it gets a little strange, because we can't really produce a complex sinusoid. If I say S equal to j omega n, then we would have something of the form A times cosine omega nt plus j sine omega nt, right? And although they're both sinusoidal, I've got this j. I've got a real part and an imaginary part. So this is something that we're just fabricating abstractly. And then we could have a decaying complex sinusoid, and this would be the case where S is equal to minus alpha plus some j omega n, right? And then we'd have the same thing as we'd have A cosine omega dt plus j sine omega dt times e to the minus alpha t. So the first two we can produce easily. The second two, that imaginary part's a little strange, but we will find this signal is useful for essentially establishing or exploring what we want to explore now. So let's consider applying this voltage to our linear elements. Okay, so we have a resistor R, capacitor C, inductor L. We have IR, VR. Now we know that the time domain relationship for the resistor is the voltage across the resistor is equal to the resistance R times IR. Okay, and so I can write IR is equal to 1 over R times VR. And if I plug in A e to the st, right, then I get an IR that is A e to the st over R, which comes back to just being this expression right here, right? I is equal to 1 over R VR. So nothing exciting here, all right? But this is kind of our baseline. It's what we already know. But things will get interesting here with the capacitor and the inductor. Now what we're after is really the simplicity that we enjoyed when we were talking about resistors. For resistors, the relationship between the voltage and the current is a proportional one. And so if you knew the current, you could calculate the voltage just by multiplying it by R. If you knew the voltage, then you could calculate the current by multiplying by 1 over R. And what we find for the capacitor and the inductor is that there's these derivatives or integrals involved. For instance, the capacitor is I equals C dvc dt. And so we don't have this nice clean, I is equal to some constant times v, or v is equal to some constant times I. And we'd love to have that. It would make things simpler. So we're going to see if that shows up if we constrain ourselves, if we discipline ourselves to a certain class of signals. The signals we're constraining ourselves to are the signals of the form a e to the st. So we discipline ourselves to use only e to the st, or a e to the st signals. Okay, we'll call this the e to the st discipline. All right, just like we had the static discipline, or we had the lumped lumped matter discipline, here we have the e to the st discipline. And we'll find that it's still pretty broad. We can solve our linear circuits with that type of, while still constraining ourselves to that discipline. So back to the capacitor. If I apply a voltage Vc that is of the form a e to the st, then when I take the derivative of it, I get an s out in front, and then I get a e to the st, which is itself just v of c. So now I can write IC is equal to S times C V of C. This is very interesting, because if you compare it to the resistance, we see that in fact we have what we were hoping for, that the current is truly just a constant away from the capacitor voltage, or vice versa. So we could write the capacitor voltage Vc is equal to 1 over Sc times Ic. All right, now let's do this for the inductor. Here we have the inductor voltage, or let's say the inductor current, sorry, is equal to 1 over L integral of the inductor voltage. And so we write IL is equal to 1 over L integral of A e to the st, right? And that gives us IL equal to 1 over S times L times basically the voltage across the inductor again. And lo and behold, we have this constant that separates, that simply differentiates I from V for the inductor. Or we can write VL is equal to S times L times IL. Now let's define impedance. All right, so this is similar, or I'll just say recall Ohm's law. We had V is equal to R times I. This was valid for, valid for all signals, or all signal forms. All right. In other words, we are not constrained. In Ohm's law, we are not constrained to a e to the st signals. All right. As opposed to for impedance. For impedance, we are constrained to a e to the st signals. In fact, impedance is defined. Impedance is defined only for e to the st signals. It has no meaning for other types of signals. So here we go. We define impedance as Z. All right, impedance Z is defined as the voltage, and here I'm going to be explicit. I'm going to say it's a signal, a function of time, but it's also a function of S divided by I, which is a function of time, or could be a function of time, and S, where V and I are of the form e to the st. All right. So let's see what the impedance is for each of these components. Incidentally, note the units of Z are ohms, just like resistance, because it's voltage over current. So for the resistance, this is trivial. Impedance of a resistor turns out to be the same thing as just the ohmic resistance. Okay. The impedance of the capacitor is equal to, and now we have to go back to our expression, and we'll go right here, right? And we're going to do V of C over I of C, and those are going to be functions of time and S, and we find from that derivation that it is 1 over SC. And for the inductor, now we're going to use this expression, and we find that it is equal to S times L. Now notice, just as a quick check here, okay, recall that a DC signal is of the form A e to the 0t, i.e. S is equal to 0, right? So let's check. Let's check if these impedance expressions for the capacitor and the inductor actually are consistent with what we know. We've been working with capacitors and inductors for a while, so we know that for a DC condition, the capacitor acts as what? As an open, right? If it's open, then its resistance, or its impedance in this case, is going to be infinite, right? An open circuit infinitely impedes current. Regardless of how much voltage you apply across it, no current will flow. So, since the impedance of the capacitor is 1 over SC, if S goes to 0, then the impedance of the capacitor goes to infinity. So let's write it this way. Z of S, a lot of times we'll write the impedance in parentheses as a function of S. For the case where the impedance S goes to 0, or I'm sorry, the value of S goes to 0, will equal or yield an impedance of infinity, i.e. it's open at DC. How about the inductor? It's the opposite. When S goes to 0, then S times L goes to 0, i.e. it's a short, as we've already found out. Okay. Now let's put impedance to work and see how it can be helpful in solving RLC circuits. Let's consider the following example. All right. Consider already the familiar RLC circuit. We'll say series. We'll do the series circuit. Okay, so we have this voltage source, Vs, and it's driving this combination of an inductor, resistance, and capacitor. All right, we've solved this before. We have a current I, we have a voltage Vs. Actually, I'll call this Is. No, I'll just call it I. Forget the I. Okay, and we're going to solve it first the conventional way. So we'll write the equations of motion, which will be written from KVL. So we go around the loop counterclockwise, or clockwise, and we have minus Vs plus VL plus I times R plus Vc. All right. Now, if I want to write this in terms of current, let's replace VL. VL is equal to L di dt, right? And we have R times I already. And then the capacitor voltage will be 1 over C, the integral of I dt. This will be equal to Vs. Now, we could take the derivative on both sides. I mean, I'll go ahead and clean this up so it looks familiar to you. If I take the derivative, if I do 1 over L times d dt, okay, from here to here, then we will have second derivative of current with respect to time plus r over L, the derivative of I with respect to t, plus 1 over LC times I, right, is equal to, it'll be 1 over L derivative of Vs. And if Vs is a constant, this will be 0 if Vs is equal to a constant, right? So we have that. That should look familiar to you. Now we try a solution. So then we try an A e to the st for the homogeneous solution. All right, we're going to focus on just the homogeneous. I'm skipping the particular at the moment. And so we'll have, we take the second derivative, we'll have S, I'll do it on both of the two equations here. So I'll have L times S times the first derivative, L times the first derivative of current, which is S A e to the st, okay, plus R A e to the st, plus 1 over C, the integral of A e to the st, which could be 1 over S times A e to the st, is equal to 0. Okay, homogeneous solution here. Or, if I use the second equation, I would have S squared A e to the st plus R over L times S A e to the st plus 1 over LC times A e to the st. Right, either one of those. And of course, then we pull out the A e to the st. This should all be good and familiar to you by now. And we can write it also this way: S squared plus R over LS plus 1 over LC A e to the st is equal to 0. So we'll stop here for a moment, okay? We'll stop here, and let's now do something a little different. Let's use our impedance. No, I'm sorry, not yet. Take that back. Fourth step, let's write the characteristic equation, which we essentially have here. What I put in parentheses is the characteristic equation. So we have SL plus R plus 1 over SC, right? And of course, for this here to be a solution, or for A e to the st to be a solution, then this equality has to be satisfied for all time. So therefore, the expression, the polynomial in S there, has to be equal to 0. All right, that's our characteristic equation. Or, we've probably written it more commonly as this. These are the same expressions, though. All right. Now let's do something a little different. Now we're going to actually write. So there's no connection to this yet. This seems a little random, but let's write the impedance. Write the impedance Z equivalent, ZEQ, looking into the RLC network. All right, what do I mean? We're going to go in here and look. So if I draw a dotted line, imagine that you're the voltage source Vs and you're saying, okay, what am I driving here? This would be the impedance we're looking for. All right. Now the impedance ZEQ, it's going to be a function of S, is equal to a combination of the impedances for each of these elements. And fortunately, adding impedances is identical to adding resistances. So they just add ZL plus ZR, which isn't a function of S, plus ZC. Okay, and if they were in parallel, they would combine in parallel just like resistances. So let's replace or plug in what the impedance is for each of these elements. It's SL, as we found, plus R, plus 1 over SC. And when we look at this, and then when we look at our characteristic equation right here, we see something very interesting. This impedance, SL plus R plus 1 over SC, is identical. Okay? Identical to the characteristic equation. To the characteristic equation. And this should be exciting. Why? Because to date, the only way we arrive at the characteristic equation is by actually writing the differential equation and then trying out AE to the ST. And here we have found another way to arrive at something that has the same, or is equivalent to the characteristic equation, but we arrived at it without having to write any differential equations. Now let's put this to use. All right. Now consider that I'm going to throw everything, my RL and C, into this box, and I'm going to call this ZEQ. All right. And I'm going to apply a voltage, Vs, across it, and there's going to be a current I that's going to flow. And the question is, what is the current I? After all, if we were solving this circuit, last week, and I asked you find the homogeneous response for this circuit, find I, you would be looking for the solution form of the current flowing through all of these. So here our task is to find I given Vs. Okay, we're going to find the complete solution here. Find I, and we'll say the complete. We're going for all of it. Complete solution given Vs. All right. Well, the beauty here is that we can write I as a function of t in general, and it's also going to be in general a function of S is equal to the voltage V of t. I'm going to write this generally because remember, all of our signals, we're in this discipline, in the sandbox, where all of the signals that we are going to excite our system with are going to fall into the form of AE to the ST. So if it turns out that Vs is just a constant 10 volts, then our term S will be 0. And then, of course, T doesn't even change that voltage at all. But in the general form, it's Vs as a function of T and S. We're going to take that voltage and we're going to divide it by the impedance. And we write Z sub S because, as we have seen before, like when we looked at the individual elements, we saw that the impedance, for instance, of the capacitor, 1 over SC, is a function of the form of the signal that you're forcing it with. If you force it with a constant voltage, i.e. S equal to 0, then the impedance is, in fact, infinite. But if you were to force it with a signal that had a very large S, then the impedance would tend towards 0. So, we're going to see how far we can carry this analogy to Ohm's law. Where after I, we have V, we can write an expression for Z. So let's look for the particular solution and then the homogeneous solution. All right, so first, the particular solution. Okay. We'll write IP, and I'm going to drop the function of T and S just to be more efficient at writing. IP, P for particular, is going to be equal to V of S, all right, divided by Z of S here, where S corresponds to the S in Vs equal A e to the ST. Okay, so let's assume a DC Vs equal to capital Vs here. So therefore, S is equal to 0. So let's solve for IP. IP is going to be equal to Vs, this constant now, capital Vs, divided by Z evaluated at 0. And what is that? I'll have 0L plus R plus 1 over 0C. Well, this last term, 1 over 0C, blows up. It goes to infinity. So I have Vs, the constant Vs divided by infinity, and therefore the current that's flowing in steady state is 0. And if you think about this, forget about impedance, just look at the circuit up here. We know that if you apply a DC voltage across this RLC series connection, you will get zero current. And the reason you'll get zero current is because the capacitor opens up. All right? If the capacitor wasn't there, then the steady state current would actually be capital Vs divided by R, but not in this case. All right, so we have our particular solution. IP is equal to 0 amps. And that was pretty easy. So now let's go on and find the homogeneous solution. Now this is a little more interesting, a little trickier maybe to visualize or conceptualize. So here's our network again. Now we're treating the case for the series RLC, but I'm writing it generally because what I'm showing you here applies to any network, any linear network, whether it was not just the series RLC. So when we have the homogeneous, when we look for the homogeneous solution, we turn off the source. Vs is equal to 0, right? We force it to 0. And now we still have this current I. Right? Now by Ohm's law, not Ohm's law, by the impedance, the Ohm's law equivalent, but for impedance, we would have Vs is equal to Z times I, right? But for the homogeneous case, Vs is equal to 0. So therefore, the only current, and this is critical for understanding this step, the only current I that can flow is one whose S value, when applied to Z sub S, yields 0 volts Vs across the impedance. Okay? What am I saying? If there is any current, what we're trying to find here, we're trying to find the current that could exist when there is no external excitation. But by Ohm's law for impedances, whatever current flows must be such that when you take that current times the impedance, you actually get 0 volts, because 0 volts is what we actually have at the input when we turn off our source. So if Vs is equal to 0, then Z equivalent times I, and here I'm going to be explicit and write as a function of time and S, then Z times I must equal 0, because it equals Vs, which is 0. How can this happen? This can only happen, except for trivial cases where I is 0, this can only happen when Z is equal to 0. Any other Z that's not 0, when multiplied by some current that itself is not 0, will produce something other than 0 volts, and that we can't have. That might exist, but not for the homogeneous case. That would exist if you were driving the system with that particular voltage. But by definition, for the homogeneous case, you're driving the system with 0 volts. So the only current that can exist is the one that when flowing through this impedance will produce 0 volts. And that can happen only if the impedance actually evaluates to 0. So therefore, find the roots for Z equivalent S equal to 0. So in our case we have, what did we have? We had SL plus R plus 1 over SC is equal to 0. And we can put this into our familiar form of S squared plus R over LS plus 1 over LC. And we see this is the characteristic equation. This is the series RLC characteristic equation, which is amazing that we could get it by actually just doing Ohm's law for impedances. So let's find the roots. The roots are, we know this by now, S1 and S2 are going to be equal to minus alpha plus or minus square root of, alpha squared minus omega n squared, or omega O squared, right? Where recall this, alpha is equal to 1/2 R over L for the series circuit, series RLC, and omega n is equal to 1 over square root of LC. So we have if alpha is greater than omega n, then the homogeneous response is 2 real exponentials. All right, it's overdamped. Overdamped. We're back to familiar ground here. If alpha is less than omega n, then homogeneous response is sinusoidal. All right, underdamped, just like before. The difference in the impedance technique is how you arrive at the characteristic equation. Let's apply this to, so we can cover some more ground. Let's apply this to the parallel RLC. Okay? So in the parallel RLC, let's say that I had this circuit here, IS, and I have in parallel an R and an L and a C, right? And I want the voltage V across here. So what would I do? I would write the voltage V is going to be equal to IS times some equivalent impedance, right? The equivalent impedance is going to be, the parallel combination of these three, R, C, and L. So it would be 1, how do we do this? It's going to be the inverse of 1 over R, right? We add the okay, well, I need to define something here. I was about ready to use a new term. Do you recall that when we talk about resistances, we also talked about conductance, right? We had conductance was equal to 1 over resistance. This is conductance. Well, in impedance, we have something similar. We define admittance. Still sounds like conductance. It admits current flow. Admittance is defined as 1 over impedance, and it's the letter Y that we use. It has units of mhos, or Siemens. And you recall when we combine resistances in parallel, we can more easily just add their conductances and then take the inverse afterwards. So let me rewrite this. We'll just say Y, the admittance, equivalent admittance, is equal to 1 over R, that's the admittance of the R, plus SC, because the impedance of the capacitor is 1 over SC, plus 1 over SL, because the impedance of the inductance is SL. We can rewrite this actually as V is equal to, instead of I times 1 over Z, we'll write as V equal Y equivalent times IS. Right? That's just like saying V equals GI. So we have V is equal to 1 over R plus SC plus 1 over SL times IS. Now, if we want to find the complete solution, right? So we'll say suppose, we can define IS. Suppose IS is equal to just some constant. That means, i.e., S is equal to 0, right? E to the 0t. This leads to a particular response of voltage as being 1 over R plus 0 times C plus 1 over 0 times L times this current I.O., right? Now what happens? This total admittance goes to infinity. Why is there infinite admittance? Think of conductivity, infinite conductivity. It's because of the inductance, right? We said at DC the inductance is a short. So if you apply a DC current to it, then it has, and the dI dt is 0, then the voltage across it is 0. And so therefore, okay, I just realized I made a big boo-boo here. Let me go back and correct my mistakes, which you probably were staring at and wondering about as I made them. This is not 1 over z, right? V is equal to I times z. So this is z equivalent. That was wrong. This is wrong. It's z equivalent. Okay. Now what I have then is, this is correct. The admittance is 1 over R plus SC plus 1 over SL. However, when I express my voltage in terms of my current, I need to do impedance times IS, or I have to do 1 over admittance, right? So this is what I need to do. And here, finally, I have to correct this. Be like this. This makes a lot more sense. Okay. So now, the admittance does blow up. That's true because the inductor is a short. So there's infinite admittance. But the voltage that results across that admittance then is 0 because the admittance it's essentially like a short. So we have 1 over infinity. Therefore, Vp is equal to 0 as we would expect. All right, let's head on to the next page and we'll look at the homogeneous response. So homogeneous response. And here we have V, see if I don't mess up here, V is equal to Z equivalent times IS, or it's equal to 1 over Y equivalent times IS. Okay, but IS is by definition 0 for the homogeneous response, or the natural response. So let me rewrite this. I'm going to write IS is equal to Y, the admittance, times V. And I'm going to write this as a function of time and S. Okay? So this is just saying the current is equal to the voltage divided by the impedance. Now, since this is the same kind of situation as we had for the series circuit. For the series circuit, though, we were saying V is equal to Z times I, and since our forcing was a voltage, we said our voltage must be 0. So I times Z must be 0, which means we need to find the zeros of the impedance. Well, here, it's the opposite. We need to find the zeros of the admittance, because the current is equal to the admittance times the voltage. And yet, by definition, we turn off the source I, and so there must be no current flowing. And the only way to do that is if Y equivalent is equal to 0. So, therefore, any voltage V that can exist when IS is equal to 0 must have a corresponding admittance Y equivalent that is equal to 0. Okay? So what is our admittance? We calculated that, or we wrote that on the previous page. It was 1 over R. Remember, we're putting all these three in parallel. 1 over R plus SC plus 1 over SL. And we're going to set that equal to 0. So find the zeros, the roots of Y equivalent. All right, so we can massage this, and we can put this into this form of that we're familiar with, S squared. So I think what I'm going to do is multiply by S over C. So S over C will get me 1 over RCS plus 1 over LC. This is exactly what we would have arrived at for a characteristic equation had we written the differential equation, say node analysis, for the parallel RLC circuit. And then we put this into the standard form, 2 alpha S plus 1 over, plus omega n squared. So this leads to an alpha equal to 1 over 2 RC, and an omega n equal to 1 over square root of LC. And let's assume that R, LC are such that the homogeneous or natural response is underdamped. Okay, so therefore we'll have the form V, I'll put H here for the homogeneous. V of H will be of the form A cosine omega dt plus B sine omega dt times e to the minus alpha t, where of course omega d is equal to the root of omega n squared minus alpha squared. And therefore the complete response is V equal to, remember 0 for the particular, this is V particular, plus, and then we have our homogeneous, just the same thing we wrote above, and there we have it. And we'd satisfy the initial conditions just like we would had we worked the problem from the differential equation end.